the GPR line. RF noise comes from many different sources: radio stations, TV stations, walkie-talkies, cell phones, military communications. The sun emits radio waves. The universe emits radio waves. The surface of the earth is immersed in radio waves at all times. So you will always see RF noise in your GPR data, even if the antenna is shielded. Now keep in mind that the RF noise is usually about 1,000 times weaker than the GPR signals we are transmitting. So you don't see RF noise until the GPR signals attenuate down to the noise level. But here's something else good to know about the noise in a GPR line. It is masking perfectly good GPR data from down deeper. For example, here is a GPR line on the left. On the right is a plot of the GPR signal strength. The GPR starts to record data just before the GPR transmitter fires. Strong, shallow reflections arrive at the receiver. These signals get weaker and weaker as they travel deeper into the subsurface and are attenuated. Finally, the GPR signals get to zero amplitude. If we look at the GPR line on the left, we see that the GPR reflections stop at about the red line, this red dashed line. This is called the depth of penetration. Wait a second. Why is this the depth of penetration if GPR signals are still present below that line? Because I forgot to include the background RF noise in the plot. When we plot that, this is what we get. So the depth of penetration with GPR is not when the GPR signals attenuate to zero. The depth of penetration is the depth at which the GPR signals, shown here in blue, attenuate down to the same level as the background noise floor, shown in yellow. In fact, external random RF noise is one of the main factors that limits GPR penetration depth. If you think about it, there's GPR signal buried in the noise. If we could eliminate or at least lower the background noise level, we would see GPR signals from deeper utilities. Now I want you to pay attention to my fancy animation that shows this concept. Notice how when the noise floor drops, we can see a deeper hyperbola in the data that we couldn't before. Stated another way, the depth of penetration will increase if we can decrease the noise floor. So how do we do this? By stacking or averaging the data. Some of you have probably heard about stacking. The ability to stack GPR data has been a part of all our GPR systems since the 1980s, so it's not new. But let's talk about what stacking can do for us. Stacking means that rather than just recording the signal every time the GPR transmitter fires, like this, fires, what we collect, what we save. We allow the transmitter to fire multiple times at one location. We then average the traces and we only record the average trace. So if we stack 2 times, we fire the transmitter once, we save the trace. We fire the transmitter a second time, save that trace. Then we average the 2 traces and we record the average of those 2 traces. If we stack 4 times, we fire the transmitter 4 times, save all 4 traces, then we record the average of those 4 traces. Same with 8 stacks. The key point here is that stacking traces multiple times and saving the average trace lowers the amount of noise, shown here as red signal, in the average trace. The more you stack GPR traces, the lower the noise, the better the GPR signal, and the deeper the depth of penetration. Here's another way of showing this concept, perhaps a better way, because it shows what actually happens when you're collecting the GPR data. Notice that the average trace